In today's lecture, we'll be covering a review of oxidation states and redox chemistry. So, tracking electrons is very important in inorganic chemistry, and this is something you'll have to know how to do in order to do well in this course. So, an electron transfer can occur in one of two ways. The first is a reduction reaction, and that's the transfer of electrons to a reactant. In this case, two protons are being reduced with two electrons to generate hydrogen gas. And you can tell that this is a reduction reaction because the electrons are on the left-hand side of the reaction or equilibrium arrows, shown here. The other type of electron transfer is an oxidation reaction, and that's where electrons are removed from a reactant. In this case, you can see zinc is being oxidized to zinc 2+, and 2 electrons are coming from this zinc 0 center. You can tell that this is an oxidation reaction because the electrons are in the product portion of the reaction, so on the right side of the reaction arrow or equilibrium arrow. A redox reaction, on the other hand, is a little bit different. It's the transfer of electrons between reactive species. So both an oxidation and a reduction are happening at the same time. In this case, you can see zinc is being oxidized to zinc 2+, much like it was here, but those two electrons are transferring to two protons, and the two protons are being reduced to hydrogen gas, much like the two protons up here were being reduced by two electrons. This is a redox reaction, and the electrons transfer to the reactant with more attraction for electrons. So in this case, the protons have more attraction for electrons than zinc metal. The oxidant in this reaction is the species that gains electrons and is reduced. The reductant is the species that loses electrons and is oxidized. In the above reaction with zinc, which is the oxidant and which is the reductant? If you answered that the protons were the oxidant and the zinc is the reductant, then you would be correct. Now, this may be the opposite way of looking at redox reactions that you were taught in the past, where you looked at what species was reduced or what species was oxidized. But in this course, these are the definitions that we'll be using of oxidant and reductant because we're looking at the reactivity of reagents. We're looking at how they react. We're not looking at what happens to them in the products. We're looking at their reactivity. So reductants are species that tend to give up electrons, and oxidants are species that tend to accept them. So it is clear that in a redox reaction, it is important to keep track of where electrons are coming from and where they're going in order to properly identify the oxidant and the reductant. One way of doing this is through the use of oxidation states or oxidation numbers. Oxidation states assign the number of electrons belonging to each atom. It is a good system to do electron bookkeeping, essentially. It's important to note, however, that oxidation states are a formalism and don't actually truly exist in a sense. In many more complicated cases, you will find that partial oxidation states are used, or that it is more accurate to describe things in terms of electron density rather than oxidation states. So that's what I mean when I say oxidation states are a formalism. It's more of a way for us to try to keep track of where electrons are coming from and where they're going. Whether or not the charge on that atom is exactly what we're assigning, that can be debated. When looking at oxidation states, or numbers for monoatomic ionic species, these are actually the easiest to assign. The oxidation state simply corresponds to the charge. For covalent species, on the other hand, oxidation states correspond to the charge the atom would have if electrons were not shared. In essence, you can do a thought experiment. So if you rip apart the covalent bond, you're assigning on which atoms the electrons would go from that covalent bond. If you look at water, if you think about pulling apart the OH bonds, where would the electrons go? What would form the most stable species? This should be relatively easy for you to answer because you've encountered this chemistry many times in the past. Water is easily deprotonated to give OH-. So formally, if you broke an OH bond, the electrons will stay on the oxygen, which is the much more electronegative atom. So it holds on to electrons much better. Oxidation states are represented by plus N or minus N, or sometimes even with Roman numerals. This is in contrast to the charges on ionic species, which are N plus or N minus. And the reason we use this convention is to help differentiate between charge and oxidation state. So, when something is oxidized, the oxidation state increases. When something is reduced, the oxidation state decreases. When assigning oxidation states, atomic properties really dictate how we do so. Atoms that hold on to electrons more tightly are given lower oxidation states because they hold on to the electrons. So that means electronegativity and electropositivity are important to know when assigning oxidation states. If an atom binds to the same atom, so like in a carbon-carbon bond, when you think of ripping apart that covalent bond, both atoms would split the electrons evenly because they are both equally good at holding on to electrons. So if you ripped apart, say, a carbon-carbon bond, you would get one electron going to one carbon and one electron going to the other. It may help to think of covalent bonds in terms of Lewis dot structures to help with assigning oxidation states initially. The octet rule is also important to keep in mind because when we determine oxidation states, we want to end up with atoms that have stable atomic configurations. So, for the molecules that I'm going to draw below, what are the oxidation states of all of the atoms? So, we're going to look at water, benzene. Keep in mind that we have hydrogen on here as well. We're going to look at hypochlorite. We're going to look at chlorite. We're going to look at chlorate. And we're going to look at perchlorate. With respect to hypochlorite, chlorite, chlorate, and perchlorate, and other polyatomic anions similar to these, you should know your naming conventions for these types of anions. So what are the oxidation states of the atoms in all of these compounds? So the hydrogen on water would be +1, and for oxygen, be -2. All of the carbons in benzene would be -1, and all of the hydrogens would be +1. For hypochlorite, the oxygen would be -2. So in order to balance the charge overall on this polyatomic anion, the chlorine must be +1. Similarly, for chlorite, the two oxygens would be -2. So in order to balance the overall charge on the polyatomic anion, the chlorine must be +3. And similarly, you can assign for chlorate being +5 for the chlorine, and then plus 7 in perchlorate. We will go over common oxidation states in the main group chemistry portion of this course. Now at this point, we're going to take a look at how to balance redox reactions. This is somewhat similar to balancing normal equations, except now you need to balance the electrons transferred as well. For this reaction between permanganate and iron 2+, the first thing to do is to determine the oxidation states of all of the atoms. In permanganate, the oxygen is -2, and because there are 4 of them, in order to balance the charge on the polyatomic anion, the manganese must be in the +7 oxidation state. The iron is an atomic cation, so the charge is the same as the oxidation state. Note that we write the oxidation state as +2 and not 2+ for the charge of the cation. The two products are also atomic cations, so we can easily assign their oxidation states, +2 and +3. Next, we split the overall reaction into two half reactions, the oxidation reaction and the reduction reaction. We can see from the oxidation states that the iron is being oxidized and the manganese is being reduced, so these would be the two half reactions. Then, you balance the atoms on each side. One issue, however, is how do we balance the oxygen atoms in the first reduction half reaction with permanganate? Well, you use water, H+, and OH- to help you balance atoms if needed depending on the conditions. For any questions, I would tell you to assume either acidic or basic conditions, which would then lead you to use either OH- or H+. In this case, we will assume acidic conditions. So we add H+ to one side of the reaction for the permanganate and H2O to the other. Then we balance the number of oxygen and hydrogen atoms. You need to make sure that in acidic conditions, you never have OH- in the reaction. One way to think of this is that under acidic conditions, any OH- produced would just get protonated to water. So if you find you need to use OH- to balance the atoms in a half reaction, just add H+ to both sides and turn the OH- into water. Similarly, for basic conditions, you would do the same sort of thing, except that you would add OH-. So you would generate water where there would be H+, and you would generate OH- on the other side of the reaction to balance it out. You can even solve these types of problems always assuming initially acidic conditions if that helps you, but keep in mind to add the OH- to both sides to get rid of all the H+ if the question says to assume basic conditions. It's really up to you, but if you solve these types of questions in this way, make sure to cancel out any water that shows up on both sides of the reactions. So anyways, moving to the reduction half reaction with permanganate, to balance the water and H+, because there are 4 oxygens in permanganate, we'll put down 4 for the water, and then to balance the hydrogens, we need to put 8 protons. Next, we need to balance the charges of these half reactions using electrons. So you add an electron to the reactant side of the reduction half reaction, and we need to use 5 electrons in order to balance the charge, because we have 8 positive charges from the protons and only 1 negative charge from the permanganate, whereas on the product side, we only have 2 positive charges. So if you add 5 electrons, the charges are balanced on both the reactant side and the product side. Similarly for iron, if we add an electron to the product side because it's an oxidation, you can balance the charge for this half reaction. But we still have one more thing to do. We need to account for the number of electrons transferred to the permanganate. The permanganate requires 5 electrons. So we need the oxidation half reaction to produce 5 electrons. But now the oxidation half reaction is no longer balanced with respect to charge. So we need to balance the charge in this way. So if you have 5 equivalents of iron 2 plus being oxidized to 5 equivalents of iron 3 plus, this generates 5 electrons, and the oxidation half reaction is now balanced with respect to charge and with the number of electrons needed to be transferred to permanganate. The last thing we need to do is add the two half reactions together to get the overall balanced equation. You should be familiar with the concept of reduction potentials already, but we will do a brief review to remind you of some of the basic concepts involved and how reduction potentials can be used to predict reactivity. As we saw in the previous slide, redox reactions can be split into two half reactions, one for reduction and one for oxidation. You can actually physically separate these two half reactions into two half cells, and if you connect them with a circuit, you can use the flow of electrons to do work. This is how you construct a battery. In a battery, the reactions at the electrodes are driven by the potential difference across the two half cells. You get oxidation at the anode and reduction at the cathode. The potential at each electrode is determined by the thermodynamic properties of the two half reactions, which can be quantitatively measured. By convention, these potentials are represented by reduction potentials, which describe a reversible reduction process as shown right here. Even for the oxidation half reaction, the potential is described using a reduction potential, which is actually the reverse of the reaction that is occurring. This is a formalism, however, and it is understood that for the oxidation half reaction, we are actually talking about the reverse process. We will see how this makes sense in the next slide. More often than not, you will encounter standard reduction potentials. These values are denoted by E0 and reflect values obtained under standard conditions. These standard conditions are somewhat arbitrarily defined, but they are linked to the reference used for all standard reduction potentials, which you will see in the next slide. So for standard conditions, this means 298 Kelvin and 1 bar of pressure. Since reduction potentials are a thermodynamic property and represent an equilibrium, they are temperature dependent. All solids must be in their standard state to be considered standard conditions, and all reactants in solution must have a concentration of 1 mole per decameter cubed. In addition, for all pH-dependent reactions, standard conditions means a pH of 0 or a pH of 14 if it is standard basic conditions, which is denoted by E0 subscript concentration of OH equals 1. It's important to note that pH 0 is the same thing as saying concentration of hydronium equal to 1 mole per decameter cubed. And pH 14 is the same as saying a concentration of hydroxide equal to 1 mole per decameter cubed. And it's because pH 0 is equivalent to 1 mole per decameter cubed, that's the reason why all concentrations of reactants need to be 1 mole per decameter cubed to be considered standard conditions. And we'll see why on the next slide. What this also means is that all standard reduction potentials are assumed to be under aqueous conditions, and if they are denoted E0 and are pH dependent and not E0 concentration of OH equals 1, you can just assume that the pH will equal 0 if it's pH dependent, because standard reduction potentials without that special subscript can be assumed to be under acidic conditions. This also means that in solvents other than water, reduction potentials change in value, and this is somewhat similar to pKa values. When looking at the overall reaction across both half cells, you can calculate the cell potential of a battery using the two half-reaction reduction potentials. If you use standard conditions, this is called the standard cell potential, or E0 cell. This can actually be calculated using this equation right here. You may notice that we subtract the reduction potential for the oxidation process right here, which accounts for the fact that we describe the oxidation process using a standard reduction potential. But we're actually interested in the reverse process. By subtracting it, this essentially reverses the reaction. And this should become a little more clear in a couple of slides. Why do we care? Why are we talking about batteries when we're interested in redox reactions? Well, one way to think of redox reactions is that they are two half-cell reactions that just happen to be occurring in the same reaction vessel. If we think of them this way, then we can use standard reduction potentials to determine the delta G of the reaction, because delta G is related to the standard cell potential of a redox reaction by the equation shown right here. In this equation, N equals the number of electrons transferred per mole of reactant. F is Faraday's constant, and the free energy, or delta G, of the reaction is in joules per mole. There are two main things to look out for when you use this equation. One is that kilojoules per mole is a more common unit that's used, so most questions will ask for your answer using this unit. Be sure to convert your answer to the right unit and don't report it in joules per mole. Second, you need to keep track of per mole of which reactant the question is asking you to answer with respect to. This could change the number of electrons transferred per mole of reactant. So that would be that N value. This should become a little more clear when we do a worked example. What makes a thermodynamically favorable reaction? A positive standard cell potential will always give a negative delta G value because of this relationship right here, negative NFE. So if you have a positive E0 cell, delta G will always be negative, which means the reaction would be spontaneous and thermodynamically favorable. If the E0 cell is negative, however, you'll have a positive delta G and the reaction will be thermodynamically unfavorable. You will often see reduction potentials listed in tables from the most negative values to the most positive values, similar to the one shown on this slide. We can use these tables to predict which reactant will act as an oxidant and which will act as a reductant in a redox reaction. The more negative the reduction potential, the more reducing the compound. The more positive the reduction potential, the more oxidizing. A good way to remember this is to remember the relationship between Gibbs free energy and potential. A positive potential gives a negative free energy and a favorable or spontaneous reaction. For lithium, the reduction potential is very negative, which would give a very positive free energy of this reduction reaction. This would mean that this reduction reaction shown right here is very unfavorable. This should also align with your knowledge of chemistry because lithium is considered a very strong reductant, so strong that it reacts with water to reduce protons to hydrogen gas. Another way to remember this is that the reduction potential of oxygen in particular is 1.23 volts, which is very positive, which means it's very easy to reduce. This should also align with your knowledge of chemistry because oxidation reactions are named oxidations because of oxygen's notorious oxidative reactivity. You should also notice some parallels between the way pKa values and reduction potentials are used. Similar to pKa's, where the compound with the lower pKa value will protonate the conjugate base of the compound with the higher pKa value, The compound with the lower reduction potential will reduce the oxidized form of the compound with the higher reduction potential. Also, you may note that the reduction of protons to give hydrogen gas has a reduction potential of 0. This is the reference reduction potential for the entire scale that we use. And because the conditions under which this reduction occurs is pH 0, that defines all other standard reduction potentials, such as 1 mole per decameter cubed for all reactants in solution, etc., etc. So it's because this is used as a reference and because this was done at pH 0, that's what defines all standard reduction potentials. There are several important implications of reduction potentials that will be important for this course. What are those implications? Why are we being taught this? The reason reduction potentials are so useful is that they can be used to predict reactivity. Moreover, when designing experiments, if you need to reduce a reactant to get a specific product, using reduction potentials will allow you to choose an appropriate reducing agent. Will the following redox reaction be thermodynamically favorable? As this question implies, we can look at reactions and determine their free energy. Using the same example as before, we can see that we have already identified the half reactions for the overall redox reaction. Most questions that I will ask will involve both balancing a redox reaction and either determining if it is thermodynamically favorable, which means you just need to find out if the cell potential is positive or negative, and then indicate how that would influence the Gibbs free energy using the equation from before. For example, if the cell potential is positive, then according to that equation, the free energy will be negative and the reaction will be spontaneous. Or I will ask you to determine the free energy of the reaction per mole of a specific reactant. So, to determine if this reaction is thermodynamically favorable, we need to find the standard reduction potentials of the half reactions. For permanganate, it's 1.49 volts. For iron 3 plus to iron 2 plus, it's 0.77 volts. And you would just find these in a table of standard reduction potentials. Then, using this equation right here, we can determine the cell potential. Because the permanganate is reduced and the iron is oxidized, we subtract 0.77 volts from 1.49 volts. This gives an overall cell potential of 0.72 volts. Since this potential is positive and the free energy of the reaction is related to cell potential through this equation, the reaction must be thermodynamically favorable because the free energy will be negative. For the specific question above, will the following redox reaction be thermodynamically favorable, you could stop right here. If, however, I asked for the free energy of the reaction per mole of permanganate, you would calculate it where n equals 5, shown right here. And that's because that's per mole of permanganate, 5 electrons are transferred. If I ask per mole of iron, on the other hand, n would equal 1, because only 1 electron is transferred per mole of iron. Solving this equation and converting to kilojoules per mole gives a free energy of minus 347.3 kilojoules per mole of permanganate. Now, this may be a little bit different from the way you were taught to solve these questions in the past. There are several different methods of solving these types of questions. One where you take your oxidation process and you actually put the negative of the reduction potential, and then you just add these two together to get your E0 cell. That is a perfectly valid way of answering these questions, and if you are more comfortable using that method, I will not take off marks as long as you get the correct answer and there's a logical progression of how you got there, I'm happy. This concludes today's review lecture, which is not meant to be comprehensive, but to remind you of concepts that you should already know, which will become important later on in the course. If anything is very new or poorly understood, I strongly encourage you to review the subject before the next class, because we will build on these fundamental concepts in this course. There are some resources available on the course website that will help you with reviewing these concepts, but please keep in mind that these are not exhaustive. And as always, there are some useful websites and resources in the links below to help with some of the material that was covered in today's lecture.